When lightning strikes a transmission line, it sends a massive electrical wave hurtling toward your most expensive equipment, the transformer. But before it can cause a catastrophic failure, it's intercepted and driven into the ground by a surge arrestor. Protecting the system requires a coordinated two-part defense strategy. First, line insulators are sized to prevent constant flashover faults along the towers. Second, the surge arrestor is calibrated to clamp any remaining spike before it reaches the transformer. Today, we are going to build a complete insulation coordination plan for a 220 kilovolt system from scratch. Designing these systems requires isolating these two protective layers and calculating their distinct tolerances against physical stress. This calculation shows our first major hurdle. Threat 1, lightning surges. Because insulators experience phase-to-earth stress, we have to scale our 220 kilovolt line-to-line voltage down. We do this by dividing by the square root of 3 before applying the impulse multiplier. That math gives us an 825 kilovolt typical impulse. Looking at standard insulation tables, a 9-disc string provides an 860 kilovolt impulse withstand. For lightning, 9 discs clear the bar. But we also have to evaluate threat 2, sustained power frequency overvoltage. This is a continuous load rather than a fast spike, requiring a multiplier of 3, which results in a 381 kilovolt threat. This leads to a technical detail that is essential for real-world reliability. For sustained overvoltage, the standard is to check against the wet flashover column. Rain heavily degrades an insulator's performance, making wet conditions the necessary baseline for our calculation. Check the 9-disc row again. Under wet conditions, it only holds off 375 kilovolts. That falls short of our 381 kilovolt requirement. To guarantee the line won't flash over during a storm, we have to bump our design up to 10 discs. Dry conditions do not represent the total operational reality. Sizing insulators correctly requires anticipating the harshest physical environment your hardware will actually face. Now we move to the second bodyguard, the arrestor. Step 1 is determining the voltage rating. We multiply our 220 kV system by a 110% safety margin, then by an effective earthing factor of 0.8. That gives us a minimum rating of 196 kilovolts. Because these components are manufactured in standard sizes, we round up to 198 kilovolts to ensure we meet the requirement. Step 2 dictates our discharge current. This handwritten calculation factors in an assumed incoming surge magnitude of 1,025 kilovolts, the 594 kilovolt residual voltage, and the line impedance. Looking at the formula, note the specific multiplier here, times 2. This is a critical factor in the physics of the system. Here is the physics of why we double that number. When an electrical surge travels down a line and hits a high impedance point, like an open-circuited transformer, it behaves like a physical wave hitting a concrete wall. It reflects backward and stacks directly on top of itself, doubling the voltage at the point of impact. Factoring in that reflection gives us a discharge current of 3.64 kiloamps, leading us to select a standard 5 kiloamp class arrestor. Without accounting for wave reflection, the resulting design would be unable to handle the actual voltage rise at the transformer terminals. For step 3, we calculate the protection margin. We need to guarantee that the transformer's 900 kilovolt basic insulation level, or BIL, is safely above the arrestor's residual clamping voltage. Take a moment to pause the video. Use a 110% safety margin factor, the 900 kilovolt BIL, and our 594 kilovolt residual variable to calculate the protection percentage yourself. Running the numbers through the margin equation, we get a final result of 37.7%. Because industry standards require a minimum protection margin of 20%, our 37.7% result verifies that the selected arrestor will successfully defend the transformer. There is one final constraint. Step 4, the maximum safe distance. An arrestor with perfect specifications can only protect the equipment within a specific physical range. The physical distance, represented by L, creates a delay. The further the distance, the more time the reflected wave has to steepen and build up additional voltage before the arrestor has a chance to clamp down. We calculate this boundary using a time fraction based on the speed of light. Effective coordination relies on 3 technical constants. You must divide line-to-line voltage by the square root of 3 for impulse stress. evaluate the system under wet conditions for sustained overvoltage, and account for the doubling effect of wave reflection. Mastering insulation coordination is about understanding how these numbers represent physical events. By accounting for weather, reflection, and distance, you can ensure that your design provides the exact level of protection required by the equipment.